All right, so here we go. So some practice with pH. So hit pause, try this. This is in Google Classroom under our acid-base unit. It says day three materials, something like that. It has this, and it also has something else that you'll need. The ionization chart for acid. So give it a try. About to give the answer, so hit pause. All right, so here goes. So what I showed you yesterday was the derivations of the formulas, but really you're gonna have that formula sheet. So, just know how to use it. pH plus POH. I really like that one. And then also, anytime you see a P in front, that means negative log of whatever it is. So the P means negative log. So we can have the pH, negative log of the H, POH, negative log of the OH. We could have pKa, pKb, pKw, which again would be negative log of each of those K values. So big one, so that's a big one. So again, we get to use the equation sheet on our exams and our test coming up, but just make sure you know how to use it. Make sure you're using it properly. So have it in front of you while you're doing these. What else do I want to add there before I do this? Good enough for right now. All right, so hydrogen ion concentration is 1.0 times 10 to the minus 3. Can you estimate the answer? We're looking for the pH in each of these. So yes, we can. The log of this would be negative 3. So the negative log of this is 3. Negative log gets us 3. Next one, though, we don't have 1 times, but we can estimate the answer. We know it's going to be a little less than 2. A little less than 2. How much less? Well, we need our calculator for that. So let me make sure I shared my screen. I'm not sure if I did, so you can see this. Okay. So we have the negative log of 2.5 times 10 to the minus 2. So this is, and like I said, just 1 decimal is good enough. There's a rule with significant digits. We don't even have to worry about it. So it has to do with the number of decimal places. So it's a bit tricky. Don't worry about it. So I have a little note here. What is the H plus? So in order to find the pH for this, so in these two we were given the H plus, and this one though we're given HCl, and so HCl is strong acid. I mean, it's not equilibrium. So if this is 5.0 times 10 to the minus 4, this is also 5.0, and so is chlorine, but chlorine doesn't affect pH. So we're going to take the negative log. So once again, we can estimate it. It's going to be a little less than 4. So the negative log of 5.0 times 10 to the minus 4, and you can see we get 3.3. We can estimate the next one. So a lot of times it is asked, is this an acidic or basic solution? So less than 7, we have an acidic solution. Greater than 7, we have a basic solution. We can estimate it's 1 again, and it's HCl again. So that means the H plus concentration is also equal to that, which means the pH is 8, which means this is a basic solution. So yeah, it's hydrochloric acid, meaning it has H plus. So how can that be a basic solution? So we're going to talk about that as we do more and more of this. Next one, though, we have hydroxide. So you can still do it in your head, but now we're going to need pH plus POH equals 14, because remember, we're looking for the pH, not the POH. So when I do the negative log of number 5, it's the OH. So the answer is not 3. The POH is 3. And so the pH is 11. pH is 11. Next one, once again, we can estimate. Now, it's not going to be 2 because that's the POH. It's going to be somewhere around 12. So when I do the negative log, so I didn't do my calculator for this one. So the negative log of 3.5 times 10 to the minus 2, that gives us 1.5. But that, once again, is the OH. So 14 minus, and we get 12.5. Once again, we're not given the OH minus directly, but instead given the strong base NaOH. The strong base NaOH is going to give us 1 hydroxide. So if this is 2.0, so is the hydroxide, 1 to 1. So I can just take the negative log again. Now again, that's OH minus though, so don't confuse that. That is probably the most common mistake of all is when you don't pay attention to how many hydroxides you get in a base and doing negative log of this number and saying that the answer, so when I do the negative log of 2.0 times 10 to the minus 3, and you can see I get 2.69, or let's say 2.7. So again, one decimal. So 2.7, that is the POH though, not the pH. This is something else I talked to my daughter last week, and she said, I kept stressing the fact that that's the most common mistake, pH, when you're given hydroxides. So you have to get the POH and subtract from 14. And she said, I kept stressing, and she said she did it wrong on her quiz anyway. So don't forget. All right, now this one's again trickier. 2 hydroxides. How's that change things? 2. Well, it's a 1 to 2 ratio. So if it's 1.0 times 10 to the minus 3, this one is, and if I just show you the stoichiometry, molar. Now moles, again, moles per liter, and that's of calcium hydroxide. In 1 calcium hydroxide, there are 2 hydroxide ions. So we have 2.0 times 10 to the minus 3 molar is the hydroxide ion. So now you can't do it in your head. It says, can you do this in your head? You can't. Because 1 times 10 to the minus 3, the negative log is 3, but 2 times 10 to the minus 3, it's not the same. And so we have to do the negative log of 2 times 10 to the minus 3. And we get 2.7. So 2.7 is the POH. You can see it's the same as the one before. So a 1.0 times 10 to the third molar CaOH is the same as 2.0 molar NaOH because there's 2 OHs. All right, now, were you able to figure this one out? So we need an ice chart. This is what I did at the end of yesterday. So I'll show you officially how to do this right now again, and then we're going to go over the rest of the notes, and then it won't be too long today. All right, so HCH3O2. This is acetic acid written in the inorganic chemistry method. And what I like to do when I do acids, I showed you, and I'm going to show you again today, is add water. Always add water to weak acids. Do with the strong acids too. So weak acids. So we get H3O plus, the hydronium ion, and we get C2H3O2, the acetate ion. All right, now this is equilibrium because it's a weak acid. It's a weak acid. So we have to do an ice chart. The initial concentration of the acetic acid is 0.1. Now we don't include water when we're doing equilibrium. And what it really is it's canceled out into the K value. 0, 0. Minus X. At equilibrium, we got 0.1 minus X. Plus X and plus X, X, and X. All right. I'm going to write the Ka expression. Now, it doesn't ask for this, but you'll see I keep stressing that when I'm showing you how to do these because you usually get a point for that for free. So just writing H3O plus, C2H3O2 minus, and HC2H3O2 every time, there's a good chance you're going to get 1 point, even if you don't know how to solve the problem. Sometimes they don't even explicitly ask for it, but they say if the Ka is written properly, then you get a point. All right, now we're given this as 1.8 times 10 to the minus 5 equals X times X, which is X squared over 0.1 minus X. Now 0.1 is 1 times 10 to the minus 1, and the K value is 1.8 times 10 to the minus 5. So we have an order of magnitude difference of 4 decimal places different. So there's a really good chance that this minus X right here is not going to matter. We're going to do a percent ionization when we're done to check that. And that's that 5% rule that we talked about with equilibrium. If it is less than 5% ionized, in other words, less than 5% of 0.1 is what X is. That means these are really small numbers. This is a valid argument to save us some time with math. Now, normally you'd have to solve the quadratic equation. And if you have a calculator that can do that, then by all means, go ahead and do it. It's not wrong if you want to solve the quadratic equation, but this is a time test. And You don't want to have to be solving the quadratic, once again, when you don't have to. All right. And if you do have a solver on your calculator, try it and you'll see, why is my calculator not coming up? What's going on here? Where'd my calculator go? All right, I don't know what's going on. My calculator's not working. So let me get my handheld. Okay, so I have 1.8 times 10 to the minus 5 times 0.1. And I get 1.8 times 10 to the minus 6 equals x squared. Square root of both sides. Now, x equals the H3O plus concentration, remember, from right here, x. So we have the square root of 1.8 times 10 to the minus 6, which is 1.3 times 10 to the minus 3. So now I know the H3O plus concentration, as long as it's not 5% ionized. So let's check that first, which I told you is, you could memorize a little formula there, which is whatever you get for x divided by the initial concentration. But really you're taking a percent. 1.3 times 10 to the minus 3 is to 0.1 as x is to 100. So we're comparing the percentage. So 1.3 times 10 to the minus 3 divided by 0.1 times 100. And this thing ionizes only 1.3%. So this is 1.3%. So this is a valid assumption that we're ignoring only because it saves us so much time with the math that it's not willing to do not worth doing the math. So now we got to finish this though, because we need to do the pH. So we know it's going to be a little less than 3. So the negative log of 1.3 times 10 to the minus 3 is 2.9. So the last one is 2.9. All right, so I want to go over that again. All right, so I'm on the next page in our packet, which is dealing with the pH scale officially. So here's the formulas. Don't use this, though. Use the equation sheet. Understand, though, that the pH scale is logarithmic. So something that has a pH of 5, which is 1 times 10 to the minus 5, right? We know that for the hydronium ion concentration. When we go to 4, that is 1 times 10 to the minus 4. So that's a 10-fold change. It got 10 times more concentrated. So when you go to 1 times 10 to the minus 3 now, that's another 10 times. So that's 100 times more concentrated. So every skip in pH is a 10-fold increase in the molarity of the H plus concentration, or going the other way, a 10-fold decrease. All right, I already did these two yesterday. I'm going to skip those. I'm going to start right down here with finding the equilibrium constant from the pH, but I left myself a little more room on the next page. So here it goes. All right, so it is a weak acid HA. So any weak acid with a general formula of HA. H being the hydrogen ion and A being any anion. As I said with the equations, I always add weak acids to water and we get H3O plus and we get A minus for the negative ion. Ice chart. Our initial concentration is 0.1. 0.1 is a popular choice, you're going to see. All right, so none of that, none of that. Minus X, so it's always 1 to 1 to 1, as I mentioned yesterday. We're always losing 1 hydrogen at a time. Even if it loses 2, it'll do 2 different equations. It'll lose 1, you can do the ice chart, and then you take those equilibrium conditions and you ionize it again to a second ice chart. And there's a second Ka value as well. There's Ka1 and Ka2 for substances that ionize twice. So 0.1 minus X. Okay. We're looking for the Ka this time. I'm going to do what I said before, which is I'm going to write the Ka expression. That's what they call this, the Ka expression or the equilibrium expression. Remember, I talked about that during equilibrium as well. We never include pure water. So now we can plug this in terms of X, but this time we don't know Ka. So how are we going to solve it? Well, just like with equilibrium, remember there were some other ways to get our answer. And one of them was they would tell us one of the equilibrium concentrations. Now they don't tell you directly on this one, but they do tell you that the pH is 4.25. So if the pH is 4.25, what is the hydronium ion concentration? So this is that equation that I gave you yesterday. It's not on our equation sheet. If you're good at logs, you can derive it yourself or memorize it, which is And the hydronium ion concentration is equal to 10 to the negative pH. So that is 10 to the negative 4.25. So I need my calculator again. Let's see if my calculator is still not cooperating. Let me see if I close it. I don't know what happened there. Close and reopen to work. So we have 10 to the 10 to the negative 4.25, and this gives us our molarity of the hydronium ion, which is X. How does that help us? Ka is equal to X times X. Now, normally we would ignore this minus X like we just did, but we don't have to in this case because we know what X is. So we don't even have to ignore it. I'm going to do both. I'm going to show you the Ka value if you do ignore it and the Ka value if you do not ignore it, and see why it's okay in those other problems generally to ignore it. At least we'll see what the answer is. Maybe it's a little too close, but all right. So what's X? Well, X is 5.6 times 10. So I'm going to plug in 5.6 times 10 to the minus 5, and I'm going to square it on the top, and then I'm going to do 0.1 minus 5.6 times 10 to the minus 5. Now think about what we're subtracting here. 0.1 minus 0.00001. So, really small amount. All right, so 5.6 times 10 to the negative 5th squared divided by, put this one in parentheses, 0.1 minus 5.6 times 10 to the negative 5. And we get 3.1 times 10 to the minus 8. And remember, K values are unitless, so we don't have to include a unit. So that's if I don't ignore this. What if I do? Just like we did in that last problem, because it's going to be really not ionized much this time. We have times 10 to the minus 8 for the K value, and the initial concentration was times 10 to the minus 1. All right, so what would it be then? So then it would be, we got 5.6 times 10 to the negative 5 squared, just divided by 0.1. And you can see we get 3.1 times 10 to the minus 8. So, doing it here isn't a big deal because we're just subtracting, but not ignoring that minus X. And the previous problem that we did over here, and this last one, if we don't ignore the minus X in this equation, then we have to solve X is equal to B squared plus or minus the square root of, oh no, I don't even remember it. Let me think. Now this is B squared minus 4AC all over 2A. I'm messing this up. I don't remember what that is, but I'd have to look it up. But yeah, we'd have to solve the quadratic equation, and we'd have to solve the quadratic equation. We get this equation into the AX squared plus BX plus C equals 0 format. Plug in A, B, and C. I can't remember what that is. Is it opposite B plus or minus? I think that might be it. Opposite A, opposite, I don't remember. But again, we don't care because we're not doing it. All right, let's do the second one here. So what is the percent? Let's do the percent on this one too, since I have it. So we have X, we have the initial. So it would be, it's always the same. X, 3.1 times 10 to the minus 8 divided by the initial concentration times 100. So you can see this ionizes 3.1 times 10 to the minus 5%. So, really, really small. Next one. Find the percent ionization of a 2.5 molar HNO3 solution. So HNO2 added to water, equilibrium. It's a weak acid. There's only one more O than H. If it's HNO3, then it's strong. It's nitric acid. This is nitrous acid. The nitrite ion, not the nitrate. Ice chart, weak, equilibrium, no water. 2.5 this time, so a pretty big concentration, and 2.5 minus X. 0 and 0, plus X and plus X, X and X. Again, always the same. It's always a 1-to-1 ratio. I always like to write the Ka expression, whether I need it or not. Just get in the habit of doing it every time, even though it's kind of tedious, because then you'll never get it wrong. All right, we're missing some information here. We need the Ka value for HNO3. Now, on the AP test, they will have it right in the problem. And on your test that you get from me, I will do the same. But sometimes in the book, they don't do that. And so we need to go to our classwork, and we need to go to the materials that I gave you today. And it is this. So acid-base ionization constants at 25 degrees. We need HNO2. Here it is. Notice that some of them have two columns because they have two hydrogens. So they have a first ionization energy and then a second ionization energy. First ionization energy, second ionization energy. H3ASO4, weak acid, first, second, and third ionization energy. All right, so we need 4.5, it's this one right here, 4.5 times 10 to the minus 4 is the, so the Ka is 4.5 times 10 to the minus 4. Now that equals x squared over 2.5 minus x. Now we're going to ignore the minus x, again, to save our math time, because otherwise we got to solve the quadratic. Got to factor it. So that equals x squared, and now we got to take the square root, and we get x equals 0.034. I'll keep both of those. So what is the, now we can find the pH, we know x, but this doesn't ask for x, it asks for the percent. So the percent is, what did you get for x over the initial concentration, like always, x over the initial concentration. What we're really finding is what percent of 2.5 is 0.034. And we get 1.36%. So this thing is 1.36% ionized, which means we can take the negative log of that number and get the pH. All right, next one. Finding the H3O of a weak acid solution again. So we're doing it again, not given the Ka value again, so I need it. So let's go find that. So the Ka of HCN this time. So hydrocyanic acid, it's right there. So 4.0 times 10 to the minus 10. HCN plus water, equilibrium, H3O plus, Cn minus. Ice chart. 0.1, none of that. 0 and 0. Minus x, 0.1 minus x plus x, and x. Ka equals, get in the habit. I'm not even scared. I have a bear running behind me. We're looking for x this time. We're looking for the H3O plus. So we have 4.0 times 10 to the minus 10 equals x over x times x, 0.1 minus x. We're definitely going to be able to ignore the minus x this time. 0.1 times 10 to the minus 10, huge difference. So we got 4.0 times 10 to the minus 10 times 0.1. That equals x squared, square root. 6.3 times 10 to the minus 6 for x. And that is exactly what we're looking for. This is the molarity of the H3O plus. I could find the pH. Negative log of that number. pH of this is 5.2. We could then check the percent ionization. So x, 6.3 times 10 to the minus 6 divided by 0.1, the initial concentration, times 100, and you get 0.0063% ionized. So not very ionized at all. All right, so same thing with the next one, and it's actually HNO2, so I'm not even going to do that one. If you want to do that one, you can. It is example 15.6 in your book, and so you can actually see them working it out. And then this little play sign there means there's actually a video that you could find online of someone doing it as well. Not me, but somebody else. All right, let's do these two for bases. What is the difference? Well, the one difference is instead of a Ka, you have a Kb. But the big one, as I said before with my daughter, is make sure you're looking for pH when you're doing it, because you're going to get the OH concentration in these. So when you get the OH concentration, you have to do 14 minus. So don't mess that up. All right, so these are strong bases. So these are easy. Because if I have 0.225 molar KOH, that means I have 0.225 molar OH minus. So I need to do the negative log of 0.225, but that is not my answer. That is, remember, negative log means the P, so that's the potential of hydroxide, which is 0.6. So then the pH is 14 minus 0.6 or 13.4. Notice also it's a pH greater than 7. If you said the pH was 0.6 and you have a base, it doesn't make sense because that's not a base, that's an acidic solution. Strontium hydroxide, we have 2 hydroxides. So I have to now multiply that concentration by 2. I showed you how the stoichiometry of that works earlier. So this is 0.003 molar OH minus, which is 3 times 10 to the minus 3 OH, which gives us a pH a little less than 3. So we can estimate the pOH, I mean. I just said it wrong. 3 times 10 to the minus 3. So there's our, once again, this is our pOH, 2.5. So 14 minus, and we get 11.5. So pH of 11.5. So strong bases are easy, just like strong acids are. So now with weak bases, we have to do an equilibrium. Now, oftentimes they will use organic bases with this. So how are you going to recognize an organic base? Well, the big one is ammonia. This is the most common one by far. That's going to be used probably 85% of the time. But there are something that contains an NH2 is called an amine, and that forms a base because you can see it adds a hydrogen and forms an NH3 plus. That's a big one. And then these things called anilines or pyridines where you just have a nitrogen. Here's another amine. So you might not have a full amine, but you could have just a nitrogen. So you can see that added a hydrogen. But the big one is they're going to give you a KB. So you know it's acting as a base, which means you should know that it's adding a hydrogen. So when I do the equation for these weak bases, if they are considered organic bases, and the only way you're going to figure that out is by doing a bunch of these and you'll recognize them, we know that that is accepting the hydrogen this time, not giving it away. So that's the first change. The second one is water was acting as a base in the other reactions with the acid. Now it's acting as an acid. And so its conjugate base is OH minus. So there's our OH minus that we need. And now it's a weak acid or a weak base. So we need an ice chart, the starting concentration. We still don't do water. Everything else is identical up until the end. And then what's different in the end? Well, we have OH minus. So we have to find pH by subtracting from 14. So I'm just filling this in. Same as an acid, I'm doing that equilibrium expression, the KB expression this time. And I don't have the KB expression listed here, but if you go to that same handout I gave you, oops, whoa. Same handout I gave you, to scroll to the other side, you have the KB. So here's those organic bases. And right at the top, we have ammonia, 1.8 times 10 to the minus 5. So the KB, 1.8 times 10 to the minus 5 equals x squared over 0.1 minus x, ignoring the minus x. 1.8 times 10 to the minus 5 times 0.1 square root x is 0.0013 molar. And that is the OH minus this time. So when I do negative log, I get 2.9, but that's the pOH. So then the pH, 14 minus 2.9, and you get 11.1. Now check the ionization to make sure that minus x was valid. So 0.1 is our initial, 1.8 times 10 to the minus 5 is our x, times 100. Oh no, I have the, sorry, x was 0.0013. I put the Ka there, sorry. Glad I caught that. I did enough of these, I'm getting bored, so hopefully you are. Hopefully you got it all figured out. If not, come and do a Zoom with me. I can help you, I promise. 1.3%. So 1.3% ionized. Yep, that means our minus x is okay. It is a valid because it's not going to change the pH if we did the quadratic equation. All right, so I would like you to go to page 5 then. So at the bottom here, you have these problems. And at the bottom of the problems, I have the answers. So check yourself. Remember when you see P in front of something, it's negative log. And so if you're given the pKa, that would be the same as given the pH. So if we're given the pH and we want to know the H plus, I'm looking at number 5 here. If I wanted the H plus, remember it is the H plus is equal to 10 to the negative pH. So this will apply to all of the pH, POH, pKa, Ka. This one is Ka and pKa. So I want to know the Ka. It's not going to be molarity this time, but Ka then would be to the negative pKa. So that's the correlation. All right, so try these. I'll give you the answers. And let me know if you need me.